Today I'm going to talk to you about oxidation-reduction reactions, or as I usually refer to them, redox reactions. And you can find this in Chapter 4 in your textbook in Section 4.9. So what is an oxidation-reduction reaction? So a redox reaction is a reaction in which electrons transfer from one reactant to another. Okay, and we're going to look at some examples of these just to make that a little bit more clear. But there are two components to an oxidation-reduction reaction. The first is oxidation, which is when something loses electrons, and reduction is when something gains electrons. So there are two little acronyms that you can use to help you remember this. So oil rig stands for oxidation is loss and reduction is gain. And Leo the lion says GER. Is the acronym for loss electrons oxidation, gain electrons reduction. Okay? So in order to determine if something has lost or gained electrons, we have a bookkeeping system that keeps track of where the electrons are. And this is a number, which we either call the oxidation number or the oxidation state. They're the same thing. And it basically assigns electrons to an atom and determines if the atom has more or less electrons than necessary, or than sort of ideal. The oxidation number of a compound is the charge it would have if all the shared electrons were assigned to the atom with the greatest attraction for those electrons. So we're just going to go through some examples of that to help make it a little bit more clear, because it's sort of a weird concept. So if an atom is all by itself, that's really easy. If it's neutral, it just has an oxidation number of 0, and if it has a charge, the oxidation number just is the charge that has. So the oxidation number in the example we have here for magnesium would be 0, and for iron it would be 0, because those are both atoms, they're not bonded to anything, they don't have a charge, so they have exactly the same number of protons and electrons. Okay, for Fe2+, the 2+ indicates that we have 2 more protons than we have electrons. So this is sort of deficient 2 electrons from neutral. So the oxidation number is +2. And then for magnesium 2+, the same thing. The oxidation number for that would be +2 as well. All right, so now we have some rules for figuring out what the oxidation number is. And I'm just going to go through them so that you know what they are, and then we'll do some examples to practice using them. So the first one is that an oxidation number of a free element is always going to be 0. So that's what I just said on the previous slide. The second one is that the oxidation number of a monatomic element is always going to be equal to its charge. So if you have something that has a 2+ charge, then its oxidation number is +2. The third is that the sum of all the oxidation numbers in a compound must be equal to 0 if the compound is neutral, or equal to the charge of the ion if it's not neutral. All right. The fourth one is that in compounds, metals have positive oxidation numbers, and in group 1A metals, it's always going to be 1+, and group 2A metals are always going to be 2+. Okay, so this goes right along with the charges that we learned at the beginning of the year, so this shouldn't be new information. And then finally, in compounds where nonmetals are assigned oxidation states according to the table that's down below, and entries at the top of the table take precedence over entries at the bottom. So one of the things you'll see is that fluorine always has an oxidation state of -1, and hydrogen always has one of +1. Okay. Oxygen almost always has an oxidation charge of -2. The only exception to this is if it's bound to something, bound to a fluorine or a hydrogen above, and those would take precedence over the -2 for the oxygen. Right? Things in group 7A almost always have a -1 oxidation state. There are a couple of exceptions. And then things in group 6A, -2, and 5A, -3. And these all go along with their charges. So the numbers should be very familiar to you and should make sense. The precedence, or the order in which you would assign them, is the only part that would be new here. Now let's do some examples so that you can get a feel for how these rules work. So the first one is SO2. All right, so if we go down the table that we had on the previous slide, oxygen would be the first thing that we have a set oxidation number for. All right, so we know the oxidation for oxygen is going to be -2. So we have 2 times -2 plus whatever the oxidation number for S is, and all of that added together has to be equal to 0. Okay, so that gives us an oxidation number for sulfur of +4. All right, and for the second one, we have copper and we have chloride. So chloride would be in group 7A, so we would assign that one first because we don't have any rules for copper. So if we know that chloride has to be -1, we have 2 of those. The total has to be 0, so we know that copper has to be +2. Right, for the third one, we have HClO2. So if H is always going to be +1, O is always going to be -2. And then chlorine is the one we don't know. So if we have +1 plus 2 times the -2 plus whatever we have for chlorine, and that all has to equal 0, then we get the value for chlorine is going to equal +3. Right? For the manganese, or the permanganate over here, we know the oxygen is going to be -2. So for 4 of those, that's -8. And then the manganese, added to that, we have to get a sum of -1. So the manganese is going to have to be +7. All right. For H2O2, this is one of the examples where oxygen is going to be different than what's on our table because hydrogen takes precedence. So we know that that's going to be +1, and we have 2 of those. Right, so if we do 2 times +1 plus 2 times whatever the oxidation number for oxygen is, then we know that that oxidation state is going to have to be -1. Right, and then the last one I have here is HNO3. So H is always +1, oxygen is going to be -2, and that leaves us with nitrogen left to find. So we have +1 plus 3 times -2 plus the nitrogen is all equal to 0 because this has no charge. So we solve that and we get the nitrogen oxidation number is equal to +5. Okay, so I went through those quickly. You can go back and look at them again or listen to me more slowly, or you could go and try to do them yourself and see if you get the same answers that I did. All right, now your notes tell you that if an oxidation number changes from products to or from reactants to products, then it must be a redox reaction. So let's take a look at some of these examples and figure out if they're redox reactions or not. Okay, so in the first one, lithium is just an atom all by itself, and so is oxygen, so they're both going to have oxidation numbers of 0. And then in our products, we have lithium oxide, which is Li2O. So we know the oxidation state of oxygen is going to be -2, and lithium is in group 1A, so it's going to have an oxidation state of +1. All right, so lithium goes from 0 to positive, oxygen goes from 0 to negative, so yes, this is a redox reaction. All right, in the second one, we have iron, which is an element, no charge, so that's going to be 0. We have oxygen, again, the same thing, 0. And then we have iron oxide here, and so we have, we don't know the oxidation state of iron, but we know the one for oxygen has to be -2. So we have 3 of those, so that gives us a -6. So then the 2 irons, they have to have each +3 in order to get a neutral atom or neutral compound. So iron goes from 0 to +3, and oxygen goes from 0 to -2. So again, this is a redox reaction. All right. In number 3, we have lead and we have nitrate. So we know nitrate altogether is going to be -1. I'm just going to leave that together for this because it's still nitrate on the other side. So you could figure out what it is for nitrogen and for oxygen, but it's not necessary. If the nitrate has a -1 total oxidation state, and there's 2 of those, then the lead must have +2. All right. Our sodium we know is going to have to be +1, and the sulfate, again, I'm going to treat that as one thing just to make it easier, is going to be -2. And then on the other side, we have lead with sulfate. Sulfate has -2, so the lead must be +2. And we have sodium and nitrate, which are +1 and -1. So nothing changed there in terms of our oxidation numbers, so this is not a redox reaction. Okay, and just a tip, this is a double displacement reaction or double replacement, and those are never going to be redox reactions. So that's one way you can tell a little more quickly. All right, and then the last one we have is CH4 plus 2O2 goes to CO2 plus 2H2O. Okay, so CH4, the hydrogens are all going to be +1, and since there are 4 of them, that must mean the carbon is -4. Right, the oxygen is going to be 0 because that's all that there is there. Right, on the other side we have oxygens here. two of them, they're going to be each -2, so that makes our carbon +4 in this case. And then we have two water molecules, so the the hydrogen here is going to be +1. There's two of them, and the oxygen is going to be -2. So in this case, lots of things changed. The hydrogen stayed the same, but the carbon went from -4 to +4, and the oxygen went from 0 to -2. So this is also a redox reaction. Okay, so this is an example of a combustion reaction, and combustion reactions are always redox reactions. All right, so that wraps up our introduction to redox. Hopefully this gives you a good sense of the kinds of reactions we're going to be using. We're going to apply these to electrochemical systems in the next chapter, which is all part of this unit, in the next lesson.